Welcome back to the interactive session of the course Viscous Fluid Flow. We begin today with the week 6 contents. So, before starting what we are going to look today, let us recapitulate what we did in the previous week. So, basically, in the previous week, that was in week 5, we looked into the time periodic. So, basically, we looked into the flow field that would be generated by a time periodic pressure driven time periodic pressure gradient. So this was our problem statement. So we said that the pressure gradient is basically a function of time with some amplitude G naught. And based on this, we tend to seek what the flow field would basically look like. So this was the idea of the problem. So we began by implementing what we learned in the scaling analysis. That is tried that. So we started by deriving the non-dimensional versions of the governing equations. So we started with the dimensional governing equation, selected the characteristic scales. For instance, in our problem, we had an imposed time scale, which is basically the omega inverse, or it's basically the angular velocity. Then we selected the radius of the pipe to be the characteristic length scale, and then we derived what would be the characteristic velocity scale of our problem. And based on this, we define the non-dimensional variables. For instance, the non-dimensional velocity, the length, the time, and so on and so forth. And what we did is using this, we derived the non-dimensional version or the non-dimensional governing equations, which basically looked something like this. So we saw that in the non-dimensional version of the governing equation, uh, all the variables of course are non-dimensional, and the parameter that we saw basically, which was alpha, so it denoted a non-dimensional number, which we said was the frequency dependent Reynolds number. And then we went on to solve this equation 2 based on the boundary conditions that we had. We use the separation of variable technique, basically keeping in mind that we seek time periodic solution. So the temporal part we know would be of the form e power I t bar, and then we substituted this form into the governing equations to get basically with the idea of converting the PDE into an ODE. And this is the ODE that we got. As we said, as we saw last week, it had two parts: one, the complementary function, and the particular integral. The particular integral in this case happened to be a straightforward solution because the right hand side, of course, came out to be a constant. So the particular integral just came out to be 1 by this I alpha squared. And then for the complementary function, we saw that we eventually get the modified Basel's. So we did a change of variable, in fact. So we did a change of variable, and then we found out that the complementary function actually came out to be the modified Basel's function. So then if we know that if we know that the equation is of the form of this modified Bessel function, then its solution would be the Bessel function of the first and second kind. And then we implemented the boundary conditions to find out the constants a1 and b1. So this was the idea of how we essentially solve the problem. And finally, we found out what would be the u hat of r, which was basically in terms of this Bessel function of the first kind. And then keeping in mind that our entire solution is just the real part of u hat of r times e power I t bar, we got how the complete velocity field would look like. So this was something that we did in the last week. We just had a brief recap of what we did. So in this week, we will look into a generalized 2D problem because you had been solving 2D problems in the lecture sessions as well, or you had been at least looking into 2D solutions like flow through a rectangular duct, triangular duct, and so on and so forth. So in the same spirit, we will look a similar kind of problem, which essentially is a 2D problem, and we will look into the solution of how to actually find out the flow field of such problems. So the problem is basically the flow field generated by a rotating porous cylinder. So if you remember, we solved the flow field that would be generated by a rotating cylinder. If you remember, we solved the problem that is the fluid dynamics of an exclusion process where the cylinders were rotating. However, in this case, there won't be any axial pressure gradient. That was something that we saw earlier in the exclusion problem. But in this case, without the we will not have the pressure gradient, but what we will have is we will have a cylinder that is rotating, but that cylinder, the rotating cylinder will be porous in nature. So the idea is that, so if now the cylinder is rotating and also it's porous, this means that we will have a velocity field in the theta direction. Also, because of the nature of its surface, we will also have a radial suction of velocity, suction or whatever you say. So the velocity, so the fluid can go in, or the fluid can come out depending on whatever problem we are looking at. So this essentially means that the problem would now be a two-dimensional problem, and we will look into like solving how to, so we look in the approach of solving these kind of problems. Okay, so I briefly lay down the problem, and I would then wait for a couple of minutes for you to understand what actually needs to be done. So as I said, the cylinder will now rotate. Let's say the cylinder rotates in the counterclockwise direction with some angular velocity omega, and also there is a radial suction because of the nature of its surface. So this means that we will now have two velocity fields, and we need to solve two equations simultaneously, and also we need to solve for the pressure here. Okay, so that's the idea. So the cylinder rotates with an angular velocity, and also there is a radial suction of the flow field. So basically, the fluids, uh, so the fluid domain would be just outside of this cylinder, maybe something like this. And because of this nature, there would be also some fluid which will basically go inside its surface. Okay, and also since the cylinder is rotating, the flow field would also move something like this with suction basically. So I hope the problem is clear. I hope the problem statement is clear. So this is basically the idea of what we are going to. So this is basically the problem that we will basically solve today. So as I said, the cylinder extends to infinity. So I will also lay down certain assumptions so as to make the algebra analytically tractable. So the cylinder extends to infinity along the z direction, which means that we have a fully developed flow in this z direction, as we have seen multiple times. This means that all the variables are independent of z. Of course, the cylinder rotates in the counterclockwise direction with omega. So since since the variables are independent of z, and as you can see, there is no actuating mechanism in the z direction, which means the z direction velocity field would be zero everywhere. And this is also obvious from the problem because the cylinder is just possessing a rotational velocity, which will be in the theta direction, plus a radial suction, which will of course be in the r direction because the suction is taking place radially. So this means there won't be any velocity field in the z direction, and that's why uj would basically be equal to 0. We will invoke the axisymmetric assumptions, which means that, so can you tell me what was basically the axisymmetric condition in cylindrical coordinate system?
By d theta equals.
Yes, exactly, which means that, so the axisymmetric assumption in cylindrical coordinate system means that whatever be the variable you are looking at, its derivative with respect to theta will always be equal to 0. Remember that this axisymmetricity differs from the coordinate system you are looking at. Okay, axisymmetric in cylindrical coordinate system is not similar to axisymmetric in spherical coordinate system. In the later classes, maybe not today, I mean in a class maybe next week or the week after that, we will look into something which is a spherical coordinate system, and we will see that axisymmetry in spherical coordinate system is not the same as that of the cylindrical coordinate system. Okay, so this is the idea, but now in this problem, of course, it's a cylindrical flow field that we are solving for, and that's why our definition of axisymmetricity would be basically this. Okay, so as I have said, there will be now two flow fields that u r and u theta, and they will now be a function of r only. uh, they will not be a function of z because basically because like there is no, so the flow field is fully developed and there is no actuating mechanism in the z direction. They will not be a function of theta as well because of the axisymmetric assumption, of course. Okay, this, so I just forgot to say this is one condition, and also one, there is one more condition, that its derivative of course with theta is 0. Also the variables will not be a function of theta. Okay, so this means that the variables will not be a function of theta. That is also one. That is the another definition of saying that the problem is axisymmetric. Okay. So so these are the assumptions that we will basically see, and yeah. So okay, these are the assumptions, and then what? So as you can see, so as the cylinder rotates, so this will disturb the flow field, which will create a disturbance flow field in the vicinity of the cylinder. But when we move far away from the cylinder, that is when r tends to infinity, the flow field is just stagnant. Okay, it's just the quiescent flow field, and this means that all the velocity components would basically decay to zero, or all the velocity components would vanish when r tends to infinity. Okay, so this is the idea, and these are the assumptions basically that we will use before formally, like, so what we need to do, I will lay the task formally. Okay, so the idea is we will use the non-dimensional approach, based on the characteristic scale, non-dimensionalize the governing equation and find out solution of the governing equations. Okay, and we will see that is like we will basically see this under certain conditions, since this is a 2D flow field. Under certain conditions, we will be able to derive closed form solutions of this problem. Okay, so this is the broad idea and the broad goal of our objective. Oh, sorry, it's the basic goal as so what we are supposed to do today. Okay, so I'll stop here for some time. If you have any doubt, you can ask me, or else I'll formally lay down what basically we need to do, and then we will begin with this problem. Okay, so I'll just write here tasks, what we need to do. But yeah, so I'll just display this, and if you have any doubts, you can ask me. So I hope that this much is clear, that this will be a 2D problem. And the simplification suggests that although this will be a 2D problem, our variables, that is ur and u theta, will just be a function of r. They will not be a function of z. The reason behind is obvious, that it is a fully developed flow and there is no actuating mechanism in the z direction. They will not be a function of theta because we are looking into an axisymmetric problem here. Okay. So with this, let's get started. So the first task that we need to do is the following. So the first tasks that the question asks us is write down the boundary conditions. Okay. The second thing is that derive the governing equations, and these governing equations are now non-dimensional. Which means I need to define certain characteristic scales. So can you tell me, based on this physical picture, how many velocity scales do we have for this problem?
2.
Yeah, exactly. So we have two velocity scales. That is simply because we have a radial suction that is defined on the surface, which is basically u, and we also have the angular velocity of the cylinder. Okay, so the idea is either we can define one velocity scale, or we can define the theta direction velocity using the scale in the theta direction, and we can define the r direction velocity using the scale in the r direction. What I mean to say is that so this is basically defined by the problem. So what they have asked us is the characteristic scale in the r direction. They have asked us to consider as the suction velocity u, and the characteristic scale in the theta direction, they have said that it would be just omega times a. Okay, so this is not so either you can choose as one of these as the characteristic scales, or you can choose the individual velocity component based on their individual characteristic scales. Okay, so this is by choice, so I would say this is by choice of the problem. And based on like whatever, however way you wish to solve this problem, you can choose your characteristic scales, as I have already said. But the question has asked us to choose the the suction velocity as the radial characteristic scales, and the angular velocity of the cylinder on its surface, which is omega times a, as the characteristic scale in the theta direction. So I hope this is clear. They also further said that the pressure would basically scale as rho times u theta c square. So this bit of information they has given to us, which means that the characteristic scale of pressure would be rho times omega square a square. Okay, and this is the characteristic scale in the r direction. This is the theta direction. This is the characteristic scale for pressure, and the length scale, that is obvious because we just have one length scale, which is basically the radius of the cylinder, which is a. Okay. So using these characteristic scales, they asked us to derive the governing equations, and then finally solve for ur and u theta. Okay, this is the final task. We will solve for ur and u theta. However, we will see that under only a special case, we can derive closed form solutions for ur and u theta. And as we will proceed with the problem, we will basically be clear about what actually we meant by this. Okay, but yeah, so this is the idea. And then once you are done solving for ur and u theta, they have also asked us to solve for the pressure field. Okay, so the final task, that is the fourth task, is to evaluate the pressure field, which is basically P. Okay, and in order to evaluate the pressure field, we also required a boundary condition on pressure. So the boundary condition, so the pressure boundary condition is that pressure when the radius tend to infinity is basically equal to P naught, which is basically the atmospheric pressure or any reference pressure that you can consider. Okay, so these are the tasks that you need to do. I'll summarize them again. First, write down the boundary conditions. You can write the boundary conditions in the dimensional form as well. Then derive the governing equations by following these characteristic scales. The idea is use these characteristic scales, define the non-dimensional variable, and then finally derive the non-dimensional governing equations, and then solve that using the boundary conditions to get the velocity field and the pressure field. So the roadmap is, I think the roadmap what we will basically follow should be clear here. Okay. So I would again stop here for quick questions. If you have any doubts, you can ask me, or else we will begin. Uh, we'll begin by systematically solving the problem. Okay. Meanwhile, if you want to draw, like if you want to have a clear look at the schematic once again, you can take a look here, which is basically in your screen. Okay. Okay. So the task one so that is very simple. So we'll begin by solving the task one, and then we'll move forward. So task one is just laying out the boundary conditions. So can you tell me the boundary conditions now? So what is ur at r equals to a? What is ur at when r tends to infinity? Okay, and what is u theta at r equals to a? And what is u theta when r tends to infinity? So these are obvious from the problem that we saw. So can you tell me what is ur at r equals to a?
Minus U.
Exactly, that's minus u. Why? Because so it's an inward suction that you can see. So it's not an inward suction. The suction means that the flow is taking place in the inward direction. So it's just because of the suction. So if there is a fluid that is coming out of the cylinder, okay, so that would have been like ur at r equal to a is just plus u. Also, I just like to highlight one thing here, that we are just interested in the flow field outside the cylinder. Okay, we are not bothered about what the fluid basically will behave when it moves inside the cylinder. So that is not something that we are not bothered about. Okay, so we are just interested in solutions where R is greater than or equal to A. Okay, so what? So I hope this is clear. So what is UR when R tends to infinity?
0.
0. This means U theta when R tends to infinity is also 0. Okay, because the flow field far away from the cylinder is stationary. Can you tell me what is U theta at R equal to A?
Omega A.
Yes, omega A. So vectorically, so yeah, this is omega A. That is correct. So vectorically, the direction is determined by something like this. So actually, what we do is U theta, let's say the velocity, and E theta is basically the what you say. E theta is basically the the I mean the unit vector. Then U theta E theta is basically omega cross ER, or in fact it's basically omega cross R. So omega, as you know, can you tell me what is the direction of omega if the cylinder rotates in a theta direction?
Counterclockwise.
Uh,
Sorry.
no. So actually, yeah, that is where the concept lies.
Positive. Positive.
Okay.
From
So there,
thumb rule.
yeah, exactly. So if the cylinder rotates in the counterclockwise direction, then the omega, the direction of the angular velocity, is actually in the z direction. So it's just the thumb rule that you need to follow. Okay. So omega is basically so this is actually equal to omega times the magnitude times Ez. Okay. And R is basically the magnitude of R, which is basically A here. Okay. Times ER. So is this clear? Why is the direction of omega
Yes.
is it? Okay, so then Ez cross Er is basically e theta. Okay, you can just derive this, or it's just obvious. So it just follow the cyclic notation. So Er cross, so it's just like, it is just something like this. So Er cross E theta is Ez, E theta cross Ez is Er, and Ez cross Er is basically equal to E theta. Okay, so it's just the cyclic that cross product notation that you basically need to do here. So it is just omega A times E theta, and that's why since this is also in the E theta direction and this is also in the E theta direction, we just write that omega U theta is basically omega times A. So I think this bit is clear to you. Okay, but nevertheless, you are right. So these are the boundary conditions. Okay, and also we need to have one more boundary condition on pressure. So it says that pressure when R tend to infinity is just P naught. That is from the problem that is from the problem statement, in fact. So now, can you tell me how many unknowns are actually we are trying to solve for? Can you tell me that?
3.
Three unknowns. So let's write that. So what are the unknowns? So by three, I think you have meant u theta, ur, and the pressure.
And pressure.
Yes. And how many equations do we have?
3.
Three equations. So what are these three equations?
Continuity equation and momentum in r and theta.
Exactly. So we have continuity plus r direction momentum and theta direction momentum, which are basically the Navier-Stokes equation. Okay. These are basically the Navier-Stokes equation. This means, fortunately, we have a closed problem that we are basically trying to solve. Okay, and yeah, so this means this hints us that a closed form solution may be possible. But today I will show you that not under all circumstances every solution or like every solution that you derive from a Navier-Stokes by solving a Navier-Stokes will always result in a closed form solution. I mean, there may be certain instances where the boundary conditions are not sufficient to give us closed form solutions. Okay, I would put that in this way, and we will see that like what I actually meant by that. All right, okay. So I hope this is clear. So now we begin with the second task. So the second task is what? So they have asked us to derive the non-dimensional governing equation. Okay. So in that constant in that context, let us see what are the characteristic scales once again. So URC, which is basically the characteristic scale in the R direction, is basically the suction velocity U. You can also take it as minus U, that won't affect much. But since, as I said, the velocity in the order of magnitude have to be in that ballpark figure, so that's why you can either take it. So you can either take it as U, you can either take it as minus U, or you can take the absolute velocity of U, okay, as your characteristic radial velocity. So now if I define a non-dimensional, let's say UR bar, as we have done it in the previous class, so UR bar would be the dimensional UR divided by URC, which means it would be UR by U. Okay. Similarly, U theta bar would be what? It would be the dimensional U theta divided by U theta C, and it would be U theta by U theta C is just omega A. Okay. Similarly, PC, they have said, is nothing but rho times U theta squared. So it is nothing. So it is rho times U theta C squared. It is rho times U theta C is omega A. So it becomes rho times omega square A square. Again, it is not necessary that you need to take this at U theta C. You can take it, you can also take it at URC. But since the problem has already stated us that you need to take the pressure scale as like this, okay, and that's why we are basically doing that. It is not a hard and fast rule that you need to take this as U theta C only. Okay. So this means the non-dimensional pressure P bar would basically look as would basically be defined as P by PC, which means this P by rho times omega squared A squared. Okay. And finally, we have the non-dimensional length scale R bar. Okay. So we have the non-dimensional length scale R bar as R by RC, and RC is basically equal to A. So this becomes R by A. Okay. All right. So we have basically defined the non-dimensional coordinates here, UR bar, okay, UR bar, U theta bar, P bar, and R bar. So the next step, what's the next step? So the next step is to invoke this into the R and theta momentum equation. So we'll begin by that. So we'll begin by writing the R momentum equation in the dimensional form first. So the simplified R momentum equation, as I have said, so now we will not write the entire equation. You are much capable now of invoking all the assumption and deriving the simplified equation. So I'll start off with the simplified equation. The simplified R momentum equation basically looks something like this. So it is rho UR times del UR by del R minus rho U theta squared by R, right? So, and this is eta, it's not eta, so this is mu, that is the dynamic viscosity, times 1 by R del R of R times del UR by del R, okay, minus UR by R squared, minus there should be this pressure gradient, which is del P by del R, of course. All right. So now you need to help me out with the non-dimensionalization. Okay. So if I non-dimensionalize this term, what would basically be so what would basically be the non-dimensionalized form of this term? Can you tell me?
Rho U square by A.
Yes, exactly. So this would be what? Rho times UR scale says URC. URC is nothing but the suction velocity U. So this becomes rho U squared by A times UR bar del UR bar by del R bar. Okay. I just remember one thing here. So since I was doing this non-dimensional and all those things, so in the last class, I asked you that. So I asked the class that. So in physics, so this was in basically in week 5. Sorry for like stating it now, but I just remembered it now. So I asked that. So can you name me a practical scenario where so as where do we see an oscillating pressure gradient? Okay. So can you? So did you think about it? Like so it's very practical, and it's with, so it's just in you only. It just so it is just A very integral part of a human being. That's the hint that I would give. So
Circulatory system.
yes.
Circulatory system, sir.
Circulatory systems. Okay, circulatory systems means, can you be specific? Like what systems? Or
Or
yes? Okay, so I'll give you the answer. It's very fascinating actually, and it's, as I said, it's within the human body. So when the heart pumps blood, so it's a periodic pressure gradient, right? So there is suction, there is there is this suction of blood, and then you pump out the blood in the arteries and veins. So actually, when you model the flow of blood through an artery, you kind of model it like an oscillating pressure gradient. Okay. So if you want to model the velocity field of flow of blood through an artery, the crude way is of like so the crude way of modeling the pressure gradient is that you can model it as an oscillating pressure gradient. Yes, it is true that since the arteries and veins, so they don't have a fixed volume, so this means that with time this height may also change with time, but a crude approximation in modeling the pressure gradient could be that you can model it as an oscillating pressure gradient. The differences of course are there. You cannot map it as a fixed diametrical length, since as we know, the arteries and veins changes their shapes. Okay, and the second thing, blood does not behave in a so you cannot model blood as a Newtonian fluid, so you cannot use the Navier-Stokes equation, so you need to use the generalized equation, which is basically the Stokes equation, where basically you write the stress as divergence of the stress term. Okay, and then you need to use this non Newtonian models. So for instance, if you want to model blood, you can use viscoelastic models like Olroyd B model. So there are many viscoelastic models. Olroyd B is a viscoelastic model. There is also something which is known as a Fanapi model. So these are various like what you say. These are various non-dimensional non-Newtonian models basically. But yeah, so in a way you can model the pressure gradients as an oscillating pressure gradient. So is it clear? Or so did you get the picture? Like, did you get a broad picture where do we basically use? I hope it is clear.
yes.
Okay. So as I've said, I'll repeat it once again. If like there is some confusion, you cannot directly model. So the idea is that you cannot directly take the pressure gradient to be like this and say that okay, the flow field inside my arteries and veins would be the solution of this problem that we solve. That is not the case, of course. But the first crude way, as I would say, is that you can model the pressure gradient like this, and then you need to increase the complexity. For instance, you need to have these non-Newtonian constitutive relations, as I have said, like the Olroyd B or the Fanapi or like the Viscous. Viscous is also a non-Newtonian constitutive relation. And you also need to take in for the account that these dimensions would also effectively change with time. So this means your R coordinate might also be a function of time or something like this. Okay. But yeah, so this is the first step into adding certain complexities. All right. Okay. Nevertheless, that was an off-topic thing, but yeah, so I wish of bringing that into our attention. Okay, so we'll begin with the tasks that we are doing. So the second term, so if you follow the non-dimensionalization of the second term, it would be rho times what it would be. So it would be rho times u theta c squared. So it will be omega squared a squared by r. Okay, and this would be u theta squared by r. All right, and here this term would be what? It would be mu. So, so what would basically come out from this term? Can you tell me? So can you tell me what basically would come out from this term?
U by A square.
Exactly. It would be u by a squared. Good. So it would basically be mu u by a squared. See, this is very simple for all the viewers. This is very simple because see, this r and this r would basically cancel. So you don't need to bother about that. There is this del r and del r here. So that's why this 1 by r squared, rc squared would come out. And also there is this ur, and that's why there would be an u that would basically come out. So that's why this becomes u by a squared, and this mu was initially there. All right. So this becomes mu u by a squared times 1 upon r bar. Of course, this would be r bar here. This will be r bar. This becomes 1 upon r bar del r bar of what? Of r bar times del u r bar by del r bar. Okay. Minus u r bar by r bar squared, basically. Minus, from this term, it would be pc by r. Pc is nothing but rho omega squared a squared. So this becomes rho times, okay, this becomes what? Rho times omega squared a squared by a, because there is this del p by del r here. There is this del p by del r here. So this would be what? This would be pc by rc into del p bar by del r bar. I hope this is clear. So this becomes del p bar by del r bar. All right, guys. So now what we will do is, this is something that we get by taking out all the characteristic variables with the constants. So now what we'll do is we will multiply the entire equation by this factor. Okay, we'll multiply this by this factor, or the inverse of this factor to be precise. So we'll multiply this by a squared by mu u. Okay. So if we do that, let's see what do we get. So we get rho u squared by a times, oops, a squared by mu u into this term. So it becomes u r bar del u r bar by del r bar. Okay. Minus the second term, which is rho omega a whole squared by a times a squared by mu u, okay, multiplied by, this is u theta bar squared by r bar, and the terms on the right hand side. So the viscous term would be just like this. So it is 1 by r bar del r bar of r bar times del u bar by del r bar. Okay. Okay, so this is the first term, and there is also one more term, which is u r bar by r bar squared, and this would be the viscous term. And also there is this pressure gradient term, which is basically what it is, minus. Okay, so it is minus what? So it is minus rho omega squared a squared by a times a squared by mu u. All right. Okay, so let's simplify this and let's see what do we get. Okay, so this a and a gets cancelled out. This u and u get cancelled out. Okay. This a and this a, of course, cancels out. All right. And what do we get? Okay, this is fine. Then this a and this a also cancel out. Then okay. So I hope the algebra is fine. Please let me know if I made any mistakes in the algebra. I'll just check it with my notes as well. All right. Okay, let's see what do we get. So the first term, if I write down the first term, so what do we have? So we have rho. So what do we have? We have rho u times a by mu. So this becomes rho u a by mu times u r bar del u r bar by del r bar minus. Let's have a look at the second term. So second term, what I will do is I will do something like this. So all right. So let's look at the second term. So what do we have basically? So we have okay, just a minute. We have rho omega a whole squared, okay, by mu times u into a. So this is something that we have. Okay. So what I will do is, okay, let's see what I can do. So I will multiply by u here, okay, and I will also multiply by u, so this becomes u squared. Okay, so I think you understood that. So in this second term, basically this term, okay, I multiplied by u and I divided by u, so this becomes u squared. I hope this is clear. Okay, and then there is this term, and we will see what basically we get. Okay, and we will see. So this would be a very nice non-dimensional number that we will get. Let's see. So it is u theta squared by r. That is the non-dimensional part. Okay, and this term would be what? This term. So the press. Oops, I missed one term here. I think this would be del p bar by del r bar. I missed this term. Sorry for that. So I'll write down with the terms on the left hand side. So let's write down the pressure. Let's write down the pressure gradient term. So this would be what? Should be minus rho omega squared a squared. Okay. Times, I think there is an a here. Okay. By mu u. All right. Okay. And similarly, here also I'll do the same exercise. I will multiply it by an u. Okay. And I divide by, sorry, I'll multiply by u on both the numerator and denominator. Okay. And that's why this become u squared. And then this term will be there. Del p bar by del r bar. All right. And then we have the viscous term. So the viscous term is basically something like this. So it is just unperturbed. It is just 1 by r bar times del r bar of r bar del u r bar by del r bar. Okay, minus this term u bar by r bar squared. Okay, so the math is a little bit involved here, but yeah, it will basically be a fruitful one. Okay, so can you tell me what basically is this?
Reynolds number.
Yeah, that is Reynolds number. So we will write it down as RE. Okay. And these blue terms, okay, this term and this term look similar. Okay, see, this is rho omega square a squared a into u by mu times u square, which is basically the same as this and this. Okay, so what I will do is I'll simplify this blue term. Okay, I'll simplify this blue term as follows. So I will write it as rho. Okay, I'll write it as rho u a by mu into omega a by u whole square. Okay. See, this is possible, right? Because I bring this rho, I bring this u, and I bring this a, and I bring this mu. Okay, which basically will give us the Reynolds number. And this basically simplifies to what? This basically simplifies to Reynolds number times omega a by u whole squared. Now, can you tell me, is this entire quantity dimensional or non-dimensional?
Non-dimensional.
Non-dimensional. And can you tell me what basically is this quantity?
Ratio of u theta c square by u r
Exactly. So this
c.
is nothing but the ratio of u theta c by u r c, of course with the square. Physically, what does it signify? So it signifies that if we choose different scales, then it signifies the strength of one scale with respect to the other scale. That is what physically it signifies. Again, I've like emphasized here that had you just chosen one single scale instead of just choosing different scales, then you will just end up getting just this Reynolds number. But in this problem, in order to have a better understanding of the different flow directions, okay, that is the flow in u theta and r direction, we have chosen the scales in such a way that once we non-dimensionalize them, we will end up having a parameter which will give us the strength of one scale with respect to the another. And that's why we will write this parameter. We will write this parameter, that is the parameter omega a by u. Okay, this omega a by u, we will write it as some u tilde, where this u tilde is the ratio of the characteristic theta direction scale to the characteristics r direction scale. So I hope this is clear. So this simplifies to the Reynolds number times u tilde squared. Okay, so let's now like systematically write down what is the non-dimensional r momentum equation. Okay, so I hope this concept is clear. So this term, the term on the this is the first term on the left hand side is Reynolds number times ur bar times del ur bar by del r bar. Okay, The other term is basically what? So it's basically minus Reynolds number times u tilde squared into u theta. Okay, let's see. So it is u theta bar squared by r bar. Okay, is equal to minus the pressure term will also have an u tilde. So this is u tilde into del p bar by del r bar plus plus what do we have? Okay. Okay, so the pressure term will have u tilde and re, of course. Forgot the re. Let's so the pressure term is what? So it is just minus re u tilde into del p bar by del r bar plus 1 by r bar del r bar of r bar del u theta del u r bar by del r bar. Okay, minus this by r bar squared. All right. So if I just divide it by the Reynolds number, okay, if I just divide it by the Reynolds number, we will just get this term basically. Or let's just write it here only. So what I will do is I will divide this entire equation by the Reynolds number, which means what? Which means we'll not have this RE here, we'll not have this RE here, we'll not have this here, and we will basically have and 1 by RE factor that is coming in here. Okay. Where again I would emphasize where your RE, that is your Reynolds number, is basically rho UA by mu, and your U tilde is nothing but the ratio of the characteristic scale in the theta direction to the R direction, which is omega A by U. All right. So this basically, so this I'll just I mean make it much smaller here. All right. So this expression that you see is nothing but the non-dimensionalized R momentum equation. Okay. All right. So a part of the second task is done. Is that so? This is basically the non-dimensionalized R momentum equation. Where so is u tilde a constant or a variable? Can you tell me? Like,
Constant.
yeah, it's a constant. It is not a function of R or it's a function of theta, because these are just constants. Omega is constant, A is constant, U is constant. So these are just constant. Okay. All right. So the next task is to write the theta momentum equation. Okay. So let's see what do we get from here. So we'll start off with the theta momentum equation. Basically, just in the interest of time. So basically, just in the interest of time, what I will do is that I will just lay out. Just 1 second. Just 1 second. I'm just checking with my notes that so far, like the solutions are correct or not. All right, I think so far, I think it's okay. I think we have done correct so far. All right. So so far we have done it correctly. So let's start off with the theta momentum equation. So again, we will, in the interest of time, we will not lay out the entire theta momentum equation, and we'll just start off from the simplified form. Okay. So the simplified form would basically look something like this. So it is rho times UR del U theta by del R, And you can get this from any like standard textbook that is always there, the Navier-Stokes equation in the r, theta, and z direction in cylindrical coordinate system. So this term, the u theta ur by r, okay, equal to mu times 1 by r into del del r of r del u theta by del r, okay, minus, there's also be a mu here because, okay, you can just write it as something like this. So you can just write it as minus u theta by r squared. Okay. So quickly, now can you tell me what basically would come out? So yeah, so what is del p by del theta? So can you tell me what is this?
0.
Yeah, this is 0 because this is x symmetric. So can you now tell me what basically would come out from this term by imposing the scales? So it would be rho. Can you tell me what basically we'll get?
U gamma, U
U.
omega.
Yes. So I think we'll get, yes. So you'll get rho u omega because this r would basically cancel out. Okay. Correct. Yeah. So we'll get rho times, yeah. Yes. Because from here we'll get a rho u. From here basically we'll get omega a, and then there would be an a here. So from here, yeah, exactly. So this is rho times u omega. Okay. And then you'll have this r ur bar into del u theta bar by del r bar plus u theta bar u r bar by r bar. Okay. All right. And what we will get from these terms, can you tell me? So you'll get
Capital
mu.
omega by A. Capital
Yes,
omega by
yes,
A.
yes. So you will get omega a divided by a squared. So you'll get u omega by a, I think. I hope I'm right in this. This is fine, right?
Yeah.
Yeah, okay, good. Okay. So then you'll get 1 by r bar del del r bar of r bar del u theta bar by del r bar minus, this would be u theta bar by r bar squared. All right. Okay. So then what do we get basically? So then I think we get the nice Reynolds number here. Why? Because this omega and omega would basically cancel out, which means if I take this term into this side, you will basically get what? So you will basically get rho ua, and this mu will basically come to the denominator, and this becomes mu. Okay. Into ur bar times, yeah, then just the other terms. I'll just write it for the sake of completeness here, plus u theta bar qr bar by r bar, and this is equal to the viscous term, which is basically 1 upon r bar del del r bar of r bar del u theta bar by del r bar. Okay. Where is it? Yeah, minus u theta by r bar squared. All right. So as you can see, this is, so what is this basically? This is nothing but the Reynolds number, as we have rightly pointed out. So this becomes what? So this becomes, so the theta momentum equation. So I'll bring the Reynolds number to the other side. So the theta momentum equation basically becomes plus u theta bar plus r bar equal to, there will be this 1 upon Reynolds number here, which should be, yes, so it would be something like this. So this would be 1 upon Reynolds number, okay, times 1 by r bar del del r bar of r bar times del u theta bar by del r bar minus u theta bar by r bar squared. All right. So we have done the second task completely so as to derive, so we have basically derived the non-dimensional r bar, sorry, r and the theta momentum equation. I would stop here for some time, where of course this Reynolds number, you know what this Reynolds number, so the Reynolds number is basically rho u a by mu. Okay, so I'll stop here for some time. Okay, but still we are left. So what do we do next? So we need to solve these equations, right? So can you tell me, are these equations linear or non-linear? So can you tell me, is this equation linear or non-linear?
Non-linear.
Yeah, it's non-linear. So that's the difference, right? So far all the problems that we have seen, luckily we have been getting linear equations. Okay, so these are easy to solve, but non-linear equations are not. So they're not, it's not so trivial to solve a non-linear equation, and that's why we will use certain techniques here. We'll use certain so the assumptions. So the idea is that the assumptions will help us basically to tackle this. But sometimes what happens is that you need to solve these nonlinear equations, and then people use certain techniques like iterations and all those things. But in this case, luckily we will see that we will eventually be solving a linear equation only, and we will basically see how we will do that. But I'll stop here for some time. Okay, if you have any doubts, you can ask me. I'll be coming in just 1 minute, so you can just also recapitulate the algebra yourself. If you have any doubts, you can ask me, and or else we'll proceed. All right, guys. So what we saw is, so I'll just name the equations here. So this is basically, let's say, equation 2. Okay, and the R momentum equation, we'll name it as what, equation 1. Okay, so what we saw is that we ended up getting, so as you can see, this is also a non-linear equation, as you can see, because you have this term ur bar times del ur by del r. So you have this term here. Other terms I see they are linear because okay, so you have this u theta squared also here. So apart from these two terms, you can see all these terms are linear, and so the idea is that we have ended up getting two non-linear equations. And so now we will basically, so can you tell me what equation did we not use yet?
Continuity.
Yeah, exactly. So let's see what, so we will use the continuity equation, and let's see what do we get. So if I use the continuity equation now, I'm invoking the fact that the z dependence and the theta dependence will not be there. So in cylindrical coordinate, the continuity equation would basically look something like this. So it will be just del del r bar. Okay, and into this becomes r bar times. Uh, Oops. I'll start off with the dimensional one only, because it's always a good practice to start off with the dimensional equation. So dimensional equation would be del del r of r times ur equal to 0, and the other terms in the theta and z direction would inevitably end up to be 0. And if I non-dimensionalize this, so basically if I just non-dimensionalize this equation, what do we get? So basically we'll get u times del del r bar of r bar times ur bar, and this is 0. And since u is not equal to 0, this means that I just have del del r bar of r bar times ur bar. I hope I'm right, and this becomes equal to 0. Okay, so now if I just break this, or if I just use the product rule of differentiation here, what I will get is I will get ur bar plus r bar times del ur bar by del r bar. Okay, and this is equal to 0. Now, since we have already said, then there is no z dependence, and we have already said that we are invoking that axisymmetric condition, which now means that ur bar is just a function of r only, right? Which means I can replace the partial derivative with the ordinary derivative. So we have done this multiple times. So this becomes ur bar plus what do we get? So it is r bar times d ur bar by dr bar, and this becomes equal to 0. Okay. So what we will do is we will just bring this term into the other side, which means what I get is we get this times ur bar by dr bar equal to minus of ur bar. Okay, and luckily we saw that. So is this form an integrable form or not? Can you tell me, like, so the idea is that can you integrate this term or not, basically?
Yes.
Exactly. So the idea is that since we can just bring this ur bar by ur this term, and this becomes minus, what do you get? So I get minus d r bar by r bar. So luckily from the continuity equation and using the fact that the r direction velocity is just a function of r, we end up getting an exact integrable form. Okay, so if I integrate this, it's very simple. You can just, so you will get basically ln r. So what you will get is you will get ln r equal ln ur equal to ln r plus some constant. So you can show that ur bar basically would be some c by this quantity. Okay, that's very simple. I hope you got what I said. So if you integrate this, you will get ln of ur, and here you will get ln of c by ur, something like this. Okay, yeah. So yes, so ln of c by, yeah. So since there is this minus sign, so we'll have a denominator term, and that we'll have a minus term, and then okay, I'll do the math, and I'll just do the math here. Just tell me if I'm right or wrong. So if you integrate this, what you will get? You will get ln of ur bar. And if you integrate this term, you will get minus ln of r bar plus ln of c. So is this right or wrong? Is this step correct or wrong? Can you tell me?
Correct.
Yeah. So this means you'll get what? You'll get ln of ur is equal to ln of c minus ln of r bar, which is just the same thing. And then what you can do is you can use this property that ln of a minus ln of b is nothing but ln of a by b, which basically becomes ln of c by r bar. And then you can just, then this just becomes what? It just becomes ur bar is just c by r bar. All right. Okay. So now at least so luckily, although we end up getting a nonlinear basically equation to solve, luckily from the continuity equation, invoking all the assumptions, we saw that, so basically we saw that we ended up getting a closed form expression of this ur term. Okay, so I hope this is clear. So how do we evaluate this c? Can you tell me now? How do we evaluate this c?
Boundary condition.
Yeah, exactly. So we impose the boundary condition. So what's the boundary condition? So at r equal to 1, or let's say r bar equal to 1, because this is non-dimensional, so what is ur bar? Can you tell me what is ur bar at r equal to 1?
1.
Actually, it should be minus 1.
Yeah, minus 1.
That is simply because yeah, so that is simply because ur is basically equal to minus u and not u, because it's suction. Okay, so this means what? This means that c will basically turn out to be equal to minus 1 if you just substitute this. So your c becomes equal to minus 1, which means your ur bar is basically minus 1 by r. Okay, so I hope this is clear to you now. So from the continuity equation, we basically got, okay, we basically got the expression for the r direction velocity. Okay, so this is nothing but the so what is this? So this is nothing but your r direction velocity component. But we are not done yet, right? Because we need two more things, the u theta and the pressure. Okay, so now can you tell me how do we calculate u theta? Based on the fact that you know what is your ur bar, uh, how do we calculate this u theta? Can you give me some hints?
Could use momentum equation.
Yes. So yes. So which momentum equation? Will we use the r momentum equation or the theta momentum equation?
Theta momentum equation is independent of pressure term,
No, but so for yeah, that is true.
but
That
it
is
is
true.
a non. Yeah,
Yes. So see, I got your point. So what you said is that if you want the pressure, we now know what is UR bar, right? We know these terms. Okay. So you are saying that we will use this UR bar in the R momentum equation to get the pressure. But this is also not known,
no,
right?
no. Yeah, theta
Yeah.
momentum equation is independent of pressure.
Yes, yes, exactly, exactly. So what you mean to say is that we will use the fact that UR bar is just minus 1 by R in the theta momentum equation. Is that what you're saying?
Yeah,
Yeah, so if I use that, so what basically I will get? So what basically are we solving for then?
u theta.
U theta, okay. So then if you get U theta from here and we know UR bar, so then how will we get pressure? That's my final question.
R moment.
R momentum, exactly. So you understand the roadmap, right? So what we did is basically we had three equations which are basically non-linear and they were coupled because UR U theta came together. We used continuity, found out the expression for UR, then use the theta momentum equation to find out the expression for U theta, which is basically this. Then substitute UR and U theta in the R momentum equation to get the expression for pressure. That's the idea. Okay. So is this clear or not? So is this clear? Okay. I hope this is clear. All right. So let's do this then. So the first idea is to obtain. So I'll write down here to obtain u theta bar. We'll substitute. We'll substitute u theta bar in. Sorry. Sorry. Just this should be ur. We'll substitute ur bar in theta momentum equation. Why theta momentum equation? Because we saw that the theta momentum equation is independent of pressure, as we have rightly pointed out in theta momentum equation. Okay, so let's do this. So if we substitute, so if we theta momentum equation is what? So this is equation 2 basically. So if we substitute, I'll not show it here again. I'll just not write down the equation. So you can see that if you substitute, your equation would basically be something like this. So it will be Reynolds number times minus 1 by r bar, which is basically ur, times du theta bar by dr bar minus q theta bar by r bar squared. Okay, and this is equal to the other terms, which is 1 by r bar d r bar of r bar times du theta bar by dr, okay, minus u theta bar by r bar squared. Okay, I hope this is clear. So all we did is in equation 2, we just substituted ur to be equal to minus 1 by r. That's all. So if I just simplify, let's see what do we get. Okay, so the first term becomes minus re by r bar. Okay, and this becomes du theta bar by dr bar minus this term becomes what? This becomes re times u theta bar by r bar squared. Okay, and this, so if I basically simplify this entire term, okay, or if I just simplify this term using the chain rule, I would just end up getting d2 u theta bar by dr bar squared. Okay, plus 1 by r bar into d q theta bar by dr bar minus, what do we get? So we get u theta bar by r bar squared. Okay, and if I just rearrange these terms, okay, you will simply end up, as you can see, you will simply end up getting something like this. So you'll get a nice ODE of this form. So you'll get a nice ODE basically which looks something like this. Just tell me if I'm correct or wrong. Okay. This is r bar. This is r bar squared. So is this expression correct or not? Can you tell me? Just check the math. So basically so what do? I bring this term here. I bring this term here. Okay, that's why this became plus. And there is this r bar here common to these terms. So this term is sorted. And I also bring this term over here. So this becomes what? So this becomes this. So this will become plus, and already there is a minus here. So this becomes re minus 1 by r bar squared multiplied by this u theta. So is this fine? So I hope this is correct,
Yeah.
right? Yeah, okay. Now let's do one thing. So if I multiply this entire equation by r bar squared, so what I'll do is I'll multiply the entire equation by r bar squared. So what do we get? This becomes r bar squared du theta bar by d r bar square plus this becomes r bar multiplied by 1 plus of re into du theta bar by dr bar plus what? So plus I have re minus 1 into u theta equal to 0. All right. So did you see any equation in your previous class of this kind of form?
Yeah.
Yeah. So what is this called? So what is this equation called?
Bessel.
Is
No,
this,
not.
yeah, is this a Bessel equation? So if do you remember we studied something called an equidimensional equation?
Yeah, yeah.
See, if you look in the dimension of this term, you look into the dimension of this term, and you look into the dimension of this term, they are just the same. Okay. So this equation, so we studied the equidimensional equation into that rotating cylinder thing that we saw. Okay, and this is the same equidimensional equation. The only difference is that we have an additional term which is this 1 plus of Reynolds number. Okay, which is nothing, which is, so this is just a mere constant and nothing else. Okay, so this is nothing but, so this equation, this is nothing but the equidimensional equation. And if this is an equidimensional equation, so do you remember what is the solution from that we take? So in order to solve an equidimensional equation, we assume u theta to be of some form.
R R
Yes,
power K.
yes, exactly. We take u theta to be of r power k. So this means this du theta bar by dr bar. So I'll do this fast because we did this previously. It is this going to be something like this. Okay, and its second derivative, which is basically this, to be something like this. All right. So what we need to do is we just need to substitute this into this equation. And in doing so, you can see that just substitute. Maybe I'll just write it as equation 3 or what. Okay. Let's name something. Let's name this equation 3. Let's name this as equation 4. Okay. And then if we substitute in equation 4, if we substitute all these terms, in substitute in equation 4, what you will see is you will end up getting something like this. So you'll end up getting k into k minus 1, that is obvious, plus the second term would be just re plus 1 times k, because it have the single derivative, and the third term would just be re minus 1. Okay, and this would be equal to 0. So if you solve for, so the idea is, if you so you'll get a quadratic equation. So so the quadratic equation would be what? It will be k square plus re times k plus re minus 1 equal to 0. That is simply because this k in with this minus 1 would basically cancel out with this one, and that's why we'll just end up getting re times k only. So the idea is, if so this is just the simplification that we did. So if you just solve for k would be what? So k would be minus of b, which is just this, plus and minus square root of b square minus 4ac, which will be b square minus 4 into re minus 1 divided by 2. So the roots of this equation would be what it is. So the k1 would be just equal to 1 if we use the plus thing, and k2 would be equal to 1 minus re. Just put a plus here, check what will you get. Just put a minus here and just check what will you get. So you'll just get the roots to be something like this. So this means that the u theta as a function of r bar. So this I'm doing it a little bit fast because we did it multiple times, yeah, of how do we solve an equidimensional equation. So your u theta bar would be, so u theta is what? It's the linear combination of this k1 and k2 roots. So it would be a1 times r power k1. So it would be a1 times 1 by r. Okay. Plus a2 times r power k2. So it would be a2 times the r bar. Okay. And this would be r bar times 1 minus re. So if I just want to write u theta bar will just be a1 by r bar plus what? Plus this is a2 times r bar into 1 minus re. Okay. All right. And we name this, let's name this as some equation. So we name this as, let's say, equation 5. All right. So now, can you tell me? So I hope, so so before proceeding, I'll just stop here for 1 or 2 minutes. I hope this is clear. If you have any questions up to this point, you can just let me know, and we will figure it out. So as I repeat, what we did is we end up getting an equidimensional equation. So the general way of solving an equidimensional equation, as you have rightly pointed out, is by like assuming. So we just assume. So what we do is we just assume u theta of this form, where k is just a constant, and then evaluate these terms. Okay, then just substitute this term into this equation basically, and then we just end up getting a quadratic equation in k, where the roots of this quadratic equation is just minus 1 and 1 minus re. Okay, and then we saw that the solution has to be a linear combination of these two terms, and that's why we just end up getting q theta bar as some a1 by r bar plus a2 by r bar into 1 minus re. All right, so we'll stop here for 1 minute. If you have any doubt, you can ask me, and then we will proceed with the important bit of the problem. Okay. All right, so if you don't have any doubts, so how do we now evaluate this a1 and a2? That of course we'll use the boundary condition on u theta. So let's see what do we have as a boundary condition on u theta. So if I now see the boundary conditions, I have that u theta bar, okay, and r bar equal to 1. So what would this be? So what is u theta bar at r bar equal to 1?
1.
Yes, exactly. So this is 1. And the second boundary condition is u theta bar when r bar goes to infinity is 0. Okay. All right. So now, can you tell me r, or like I put the question in this way, can you tell me, can we uniquely get this constant a1 a2 just by using these two boundary conditions for an arbitrary Reynolds number? Because we know that Reynolds number is just a number and it can take any values basically. Of course, it cannot take a negative value, it will take a value, let's say from 0 to infinity. Or there is some problem
For
with this, yeah, or there is some problem with this boundary condition, or the idea is this bound, are these boundary condition sufficient to uniquely determine a1 or a2? Yeah, go on.
for Reynolds number greater than 1,
Yes,
A2 A2 will also be non-zero.
exactly.
A2 can also be non-zero.
Exactly. This means a2 can also be non-zero. This means that you just hinted in the right direction, and in fact you just said 90% of the answer. So what she said is that if my Reynolds number is greater than 1, then a2 can be any arbitrary value, right? This will always satisfy this boundary condition. Okay, is that what you said?
Yeah,
Yeah, so this means that solely by using this boundary condition is not sufficient to find out this arbitrary a1 and a2. That is obvious, right? We just have one condition, okay? Because this condition will not give me this a1 and a2, okay? Because this, so when RE is basically greater than 1, this is trivially satisfied, right? So this means I just have one condition and I just need to figure out two constants a1 and a2. Okay, so we cannot, in other sense, we cannot uniquely determine the solution of this problem for RE greater than 1. That's the main drawback of this analysis. Okay, so for RE greater than 1, okay, we cannot uniquely determine, we cannot uniquely determine the constants A1 and A2. But for a special case, let us now consider the other way. What happens when RE becomes very much less than 1? Okay, then can you tell me what should be the value of A2 when RD is very much less than 1? Let's say we have RE equal to 0.01. Okay, then what should be the value of A2 for this boundary condition to be satisfied?
0.
Exactly. So this is obvious, right? Because let's say if my RE is 0.01, then this R bar is basically a quantity which is greater than 1. Okay, which means that if I want, so this means that, so the idea is that R bar would basically grow when R bar increases. Okay, so or I mean this quantity would basically monotonically increase when R bar increases, which means the only way I can have a zero velocity at far field is by, so the only way is that A2 has to be equal to 0, or else this boundary condition will not be satisfied. Okay, and that you have rightly pointed out. Okay, so for R bar very much less than 1, A2 has to be, I'll just write A2 has to be equal to 0. Okay, so this should be satisfied for, so why this should be satisfied for boundary condition 2 to whole good. Okay, this means only in a special case, this means only in a special case when I have a low Reynolds number flow, I can uniquely determine the solution for A1 and A2. And in this case, A2 has to be equal to 0 for RE tending, so for, let's say I'll just write RE very much less than 1. Okay, so I hope this concept is basically clear to you. Okay, so let's now determine A1. So for A1, we will just use the first boundary condition. So the first boundary condition give us that u theta bar at r bar equal to 1 is basically 1, which means what? Which means that A1 basically become equal to 1, and that's why u theta bar is just 1 upon 1 by r bar, when, but what is the condition? When RE is very much less than 1. So is this concept clear or not to everyone? Or or you have some doubts? And can you tell me what are these kinds of flows called? So there's a special name for these kind of flows. Yeah, go on.
Viscous flow, very
Yeah, yeah, they are called high viscous
highly
flows. Yes,
highly.
highly viscous flows, or they are also sometimes known as creeping flows. Okay, they are also sometimes known as creeping flows. So if someone says that we are in the creeping flow limit, this means that Reynolds number is very much less than 1, or you can say in the limiting case, Reynolds number tends to 0. Okay, and such flows are basically known as creeping flows. The beauty of creeping flows is that it turns the like non-linear complicated Navier-Stokes equation into a linear equation. Okay, they are basically known as the Stokes equation. As so in maybe in the next class or the next to next class, we will do some analysis on creeping flows as well. But yeah, so this is the idea of creeping flows. So can you tell me which term in the Navier-Stokes equation disappears if we invoke the creeping flow limit? Can you tell me? So the hint is here only.
Viscous terms.
So the
Or
viscous term disappears.
no, no. At higher Reynolds number display.
Yes. So the creeping flow limit is at a lower Reynolds number, right? Or this means that Reynolds number tends to 0. So the question is which term in the Navier-Stokes equation disappear? Okay. I mean, which term will not be there if we invoke this?
Advection terms.
Yeah, the inertia term won't be there. Okay. And that actually is the inertia term which adds to the nonlinearity of the Navier-Stokes equation. All other terms, let's say we don't regard, so we disregard the body force as of now. Or let's say if we have a body force, it is known. Okay, then what do we have? We have the pressure gradient, which is linear. We have the we have the viscous term, that is nothing but a divergence of stress term. That is also a linear term, at least in Newtonian fluids, which basically simplifies to del square V. So all I'm saying that all other terms are either known or they are linear in nature. It is only the advection term which adds to the nonlinearity of the problem. So in the creeping flow limit, you can rest assured be said that your Navier-Stokes equation is basically a linear equation. Okay, all right. So I hope this is clear, and I hope in the context of this problem you are clear in what cases do we get a closed form solution of this problem. So this means we now have u theta also as 1 by r, and what was ur? So ur bar was basically equal to minus 1 by r bar. Okay, so we have this u theta and ur bar. So now what is left? The final task. Can you tell me what is left?
Pressure.
Yeah, the pressure
Field.
term. Yes, exactly. So we are just left with the pressure term. So for the pressure term, so what we will do is we'll insert, as we have said before, we'll insert ur bar and u theta bar in equation. Basically, I think that is 1, which is the r momentum equation. So let's insert. So the r momentum equation is too far from here. So what was the r momentum equation? So this was the r momentum equation. Okay. So we'll just insert we will just basically insert this. So we'll basically insert this ur bar and u theta bar into this r momentum equation to get an equal to, so basically to solve for this pressure term. Okay, so we will do this. So we'll not do this today as we are running short of time. So we'll do this in the next class, which is basically some steps that we need to do to calculate the pressure. And basically we will summarize this problem and we'll begin with the next topic that we will discuss. Okay, so we'll do this in the next class and then we will formally summarize this problem because it's a big problem that we solve. But yeah, so this is one kind of problem where a 2D flow basically can be solvable by invoking certain assumptions, and in the limiting case that we have basically saw here, which is the case when we invoke the creeping flow assumption. All right, guys, if you have any doubts, you can ask, or else we will proceed this problem with the last part. So we'll proceed into solving the pressure part in the next class. So,
Uh, how do we get the solution when Reynolds number is greater
yeah,
than
so
1?
that's a good question. So, in that case, in that case, basically, what you will need to do is you will need to solve this problem numerically, according to me, because analytically, I don't think so. You can basically solve this problem. So, so let's see, where do we have? So I think, yeah. So we just end up getting this one. Okay. So now if your Reynolds number is basically greater than 1, which means that this is just some 1 by, so let's say this term becomes equal to -2, which this term becomes 1 by -1. So it just becomes 1 by r squared, okay? And then you have a boundary condition here, which is not sufficient. So either you need to have some other boundary condition, okay? That is one point. Some other boundary condition means like maybe you can have a bound, okay. Hmm. Okay, I'll have to think about it. So exactly do we, so first of all, like analytically we will not get, so you must appreciate that analytically we will not get like closed form solution when you will have Reynolds number greater than one. Okay. I'm just thinking numerically, can you just solve this problem? Numerically means you using like some finite difference technique or something like this. I'm just thinking if you can find a solution or not. But that's a good question. I'll think about it. Uh, so I'll think about it basically, and I'll let you know in the next class. So that's what I can say as of now. I have to think about it. Like, how do we like solve this problem in some other way if you want to get the idea of that u theta velocity profile. I hope this is fine to you.
Okay.
All right. So maybe you can use some other techniques as well, but I don't know that as of now. But anyway, I will see it in the literature and I'll try to come up with the answer in the next class. Right? How do we like go on in this problem for Reynolds number greater than one or for inertia dominated flows on this context? All right, guys. If you have any other questions, you can ask, or like we will call it a day this time, and we'll proceed in the next week of this course. So yeah, so just to summarize that, so we have just evaluated this u theta and u r bar, invoking the fact that our Reynolds number is very much less than one, and then now as a final step, in order to evaluate pressure, we will insert this u r and u theta expressions in the r momentum equation to obtain the solution for pressure. That's what we will basically do in the next class, and then we'll begin into solving a new topic. So we'll begin something which is known as the lubrication theory, and in lubrication theory we'll see something which are basically called the creeping flow analysis, as we have saw. So we have basically like learned this year. So when Reynolds number is very much less than one, so the flows of such nature is basically known as creeping flows. So we'll see things like that in the next class, hopefully. All right. If you don't have any doubt, I will end this meeting and we'll meet in the next week. Thank you for attending the meeting. I will end it here. So I'm closing the meet now.